Today, on behalf of Mexico Hyper-Kamiokande collaboration, I will talk about the design, manufacturing, and installation of a multi-PMT vessel for Hyper-Kamiokande. I don't know, this doesn't change. Welcome. Okay. Um, in this presentation, first I am going to make a little introduction about what is Hyper-Kamiokande, although you already know what is because the conference of Saul Quen and um, my compañeras, Monse and Judith online. Then I will cover the mechanical design, metrology, testing of support and packaging, and the fabrication of the reflector rings and the characterization of a PMT. Well, Hyper-Kamiokande, also known as Hyper-K or HK, is a Cherenkov detector filled with 260,000 metric tons of ultra-pure water. This tank will detect neutrinos from accelerators, supernova, and solar neutrinos. It also will explore the CP relation in the neutrino oscillations, determine the mass hierarchy, and investigate the proton decay. At the interior of the detector, we have 800 multi-PMTs, known as multi-PMT optical modules. And each multi-PMT has 19 3-inch photomultiplier tubes known as PMTs. You can see in this image. For the mechanical design, we initially created a 3D model of the multi-PMT vessel using SolidWorks. With this model, we conduct computational simulations to analyze the stress resulting of the hydrostatic pressure that the vessel will experience. The objectives of making these simulations were to identify the weaknesses in the design and analyze the results of using other materials. Well, the analysis allow us to identify possible weaknesses in the different pieces of the multi-PMT vessel. In this image, you can see the acrylic dome, the cylinder, the clamp ring, the PMT vessel, and the backplate. You can see the red and yellow areas, and highlighting more the edge of the acrylic dome because it is the component that receives of the hydrostatic pressure. And in the unions of the PMT vessel, you can see these little areas where reinforcement can be designed for a better support. Additionally, we make more simulations using alternative materials to assess their withstand to the hydrostatic pressure to see if they can be better than the materials that the international collaboration are currently using. These three tables displays all the materials that we simulated for the different pieces in the buckling, stress, and deformation test in SolidWorks. In the buckling test table, the load factor is specified. This factor indicates that it is greater than 1, then the buckling is not expected. The stress test table compares each material's elastic limit with the maximum limit that we found in the simulations. And in the deformation test, the maximum value of deformation is shown. In general, we can see that for the dome, either of the material tested is the best, the general purpose acrylic resin or the Rome acrylite. For the PMT vessel, um, was the PETG material. For the cylinder was the HDPE. And for the backplate and clamping ring was the stainless steel AC304. We also perform a metrology of the pieces of the multi-PMT vessel using digital and analog verniers, rulers, and flexometers. Uh, the average of all the measurements taken was obtained and compared with the SolidWorks model as a reference. And we confirmed that the dimensions were close to the model to initiate the correct fabrication of the PMT vessel in 3D printing. Okay. Moreover, the researchers of the Mexico collaboration conduct testing for support and packaging for the multi-PMT vessel at Tecnológico de Monterrey, Campus Aguascalientes, Mexico. And for the support testing, these three installation positions were tested. The top and bottom positions refers to the top and bottom in the detector tank. And the three position is the barrel that refers to the installation in the tank walls. The results of this test were successful. And for the shipping packaging test, were performed in this prototype with a personal multi-PMT vessel inside. And these three main tests were of vibrations, compression, and humidity. In the vibrating table, frequencies were applied based on transport frequencies. And then the compression piston were applied to the prototype to evaluate if the box can withstand the stowage. And finally, the humidity chamber were applied different humidity and temperature levels. And the results of this test show us that the model can resist the maximum weight and vibrations. Well, during the project development, two topics emerged, and one of those was the fabrication of the reflector rings. And guided by the current layout of multi-PMT technical note volume 5, we fabricated uh, 6 reflector rings in 2D with 26 gauge aluminum sheet and 0.46 millimeter thickness in a plasma cutter. But the results were partially successful because the challenges to achieve optimal surface finishes. And finally, the other topic was the characterization of PMT. This was made by the engineer Rodrigo Medina, and he proposed electrical arrangement to ensure the correct operation of the PMT, and also make optical arrangement. You can see here uh, the black box. Here is the PMT. This is a laser to make a single photon experiment to characterize it. And this is the beginning. So, yeah. So in conclusion, the work done by the Mexican students and researchers contribute to the development of the project and set the stage for more in-depth analysis on various topics, which could lead to improvement proposals. So thank you so much. If you want to know more about the Mexico contribution in Hyper-Kamiokande, you can scan this QR that is of Outreach Hyper-Kamiokande Mexico. Thank you.
Thank you very much, Brenda. We have some time for questions. Yes, please.
Thank you for your presentation. So if the dome that you're creating is to prevent this kind of accident that happened in the past, right, when it all exploded, have you tried to characterize by how much it would affect the PMTs? Does it at all, or do you know? Like the amount of light you collect with the PMTs, you have the dome now in front of it. Does it change something significantly? Yeah.
If I understand your question is about that, if the characterization of the PMT will be different with the dome and with the dome.
Exactly.
Yeah, I don't know how to respond that question because this was made by my partner Rodrigo Medina. But it's an interesting question. But the thing is that this is initial arrangement. They will be a topic, a question that will be emerge in the future, I think. But this is just the start. Okay. So yeah, thank you.
So the material for the acrylic dome was selected and was already tested for the mechanical lighting to maximize it. So yeah, you're right on point. Yeah, we were taking precautions for that. Yeah.
Question related to it. First of all, I would like to know how thick is actually the acrylic dome? It's a centimeter too, or how thick is it?
Yeah, well, the Dr. Quinn says that is Tom.
It's like an inch.
Yeah, yeah.
So
We in the metrology.
It's really massive, yeah, because of the pressure. And now my question is there any aging here? Because you can assume that the Hyper-Kamiokande is probably going to run for 20 years. And acrylic material, I thought, gets more brittle with the time. Do you account for aging in your measurements?
Well, that is one of the challenges that Hyper-Kamiokande wants to solve. I don't know see if so when.
One of the things they're doing it's between the acrylic dome and the PMTs, there's going to be this layer of optic grease. It's gel. Yes. It's going to solidify, and the thing that people is doing to be sure it's not going to be messed up after 20 years, they're trying to accelerate the aging by putting it into higher temperatures for longer periods of times. And so far, we believe it's going to be okay, but we'll see. But we're looking into that for sure. Yeah.
So that's why we are making a lot of testing.
Okay, thanks.
Well, I have one last question. Well, maybe. Okay, there is another question with that.
Yeah.
No, I was wondering for SWJO, we're also looking at this kind of modules as one of the options. And there we're discussing between the two possibilities, either optical gel or the possibility if you can expose the PMT surface directly. Those are much smaller than these really big PMTs, so you probably have much less of a risk of an implosion with those. Plus, the kinetic energy, the energy stored because the vacuum is much smaller, is much less of a risk, even if one breaks, that you get a shock wave. So I was wondering if you could consider for your case too, to basically seal the PMTs at the support and have the photocathode directly exposed to the water instead of having the acrylic vessel. I mean, it's done in Super K by having them directly in water. We know that for much smaller water triangle detectors like Hawk Web, this works really well. Obviously, we don't have the same pressure because no, but I know some of the stuff because the SWGO collaborators are working with some of the super and hyper KP. But what I know is that the PMTs, you don't necessarily put them in an acrylic vessel or in a dome vessel at these sizes. If you go to really deep underwater thing, you put them in a vessel. So I don't know if you're at the depth and size where it's absolutely necessary, or if you could have a direct exposure to water.
This big disaster that happened years ago, the PMTs were exposed directly to water back then, right? And when that accident happened, the collaboration decided to put covers, right? And I think that's just as simple as that. So this next time they're gonna do it, they're not gonna risk it, right? Just gonna go directly with covers. Obviously, there might be ideas to just put it back again, just put it into water, but collaboration won't risk it again. I think that's my feeling from people. And I'm not expert in, there's two types of PMTs that are gonna be put there: the 50-centimeter ones, the big ones, and the multi-PMT ones. And I'm more focused on that one. And obviously that one needs to be sealed. Yeah. Thanks for your question. Yeah.
Yeah, well, I want to add that if I'm not wrong, the international collaboration in this document, this one, explain a lot of what is currently doing, and them explain that tests will be performed in water. I don't know how many water, but they will be submerged multi-PMT. So yeah.
Questions? I have just last one question. Have you taken into account the effect of earthquakes?
Sorry, what?
The effect
Ah,
of
earthquakes?
earthquakes of
Yeah.
the structure?
Yeah, in the testing of shipping packaging, in the vibrating table, the researchers make different frequencies, main of the transport, because this is the shipping packaging. But they see, yeah, they also make actually this structure of the support testing is also in the brain table. So yeah, they also tested with frequencies of
Okay, thank you very much. Then we thank to Medina for her presentation. And then we close the afternoon session. So I don't know if there are some instructions to give. Yes.
So as you know, there's going to be the talk of Professor Tink at 6, like in half an hour. And the other one was about the dinner. It's going to be held at 7:45 in the hall next door. So if you want to go, we'll see you there. That's it. 7:45. No, Professor Tink
in the hall.
half an hour.
how.
Hour and a half. Yeah, sorry. Yeah, sure. Thank you.